So in the Laplace transforms from the previous video, we learned that if you have f of t, a time domain function, by using this function, we can transfer that into S domain. That's what it is, Laplace transformation. Okay, this is what we learn in mathematics. In math, if you get a f of t, by using this integration, you have to convert that into S domain. It's a very long process. In circuits, in this class, we're not going to look into that. I'm going to provide this table, so you can have this table for the exam also. Okay, I do not remember posting this on the blackboard, but I'll post it right now after this video, so you will have access to this. So what we know, if a function is e to the power of at, then the Laplace transformation, once you convert that into S domain, that value is 1 over S minus a. Like that, for every function you have the values. We're going to use this a lot. We're going to use this a lot. This one, this one, this, these functions, we're going to use them a lot. Okay, so keep it in mind. But I'm going to post this on the blackboard. Now, going back to our previous video, there are basically 7 basic properties. By using the properties and by using the table which I showed you, Laplace transform table, we're going to convert the functions, time domain functions, into the frequency domain or S domain. Okay, that's what we're going to do. So the first one, there are 7 functions, 7 properties. Actually, there are more than 7, but these are the 7 most important ones I'm going to talk about. Okay, the first one is linear property. Okay, it's just linear. If you have a1 f1 of t, a2 f2 of t, now what we can do, find out f of s for this, find out f of s for this, and these constants are going to be multiplied on the other side, the linear property. Okay, next one is scaling property. If you have f of at in time domain, we can write this as 1 over a f of s over a. Okay, once we're solving examples, probably you will understand better how to use these properties. Okay, so you need to remember, I wouldn't say remember the properties, but you need to have good grasp of these properties. Which property should we use and where to use those things. The next one is time shift property. Laplace transform of f of t minus a, u of t minus a. U of t minus a, u of t is a unit step function. I'll talk about it. Then we can write that as e to the power of minus as f of s. Frequency shift property, e to the power of minus at f of t, we can write it as f of s plus a. This u of t, let me talk about unit step function. Unit step function is nothing but u of t, the magnitude is going to change to 1 at 0. Okay, so this is time, that magnitude is 1, y-axis is u of t. Until 0, that magnitude is 0. At 0, the magnitude is changing to 1. It's just like we are turning on the switch or turning off the switch. Okay, when you turn on the switch, now the current value or voltage value is going to change from 0 to certain value. So that's what it indicates. That's what the unit step function indicates. Okay, so unit step function indicates what happened after switch is closed or open. Okay, after something happened in the circuit. So that's what unit step function represents. Time differentiation property. Okay, so time differentiation property, if you have d to the power of n f of t over d to the power of n, then you can write an equation in this format. I'm not going to say that, but see that equation. Now the next one is time integration property. If you have integral of f of x dx from 0 to t, we can write this as 1 over s f of s. Frequency differentiation property. So in frequency differentiation property, Laplace transform of t times f of t, we can write that as minus df of s by ds, or if you have t to the power of n f of t minus 1 to the power of n d to the power of n f of s by ds. This is the frequency differentiation property. So these are the 7 properties we're going to use a lot. Okay, by using these properties we can solve an example. So we're not going to use this equation to transform time domain equation to frequency domain equation. By using these properties and the Laplace transform table, we're going to transfer the given time domain equation into frequency domain. So here is a first example. We have f of t equal to cos 2t plus e to the power of minus 4t times u of t. So as I mentioned, u of t indicates that magnitude is changing from 0 to 1 at t equal to 0. That's what u of t indicates. So don't worry, even if you don't have u of t, still f of t equal to cos 2t plus e to the power of minus 4t. It's not going to make big difference if you have u of t or not. U of t indicates after switch is closed or open at t equal to 0. That's what it indicates. So if I don't have it, probably I might be talking about somewhere here. So the switch hasn't been changed. It has been closed for a long time, or it has been open for a long time. We don't know. We'll take that as 1. Okay, if we don't have u of t, that's what it is. Now, so I mean, by using the linear property, you can see I can find out Laplace transformation of this from the table, and then I can combine them. So Laplace transformation of cos 2t is nothing but, I'm going to show you the table. So Laplace transformation of cos, see here, cos at is nothing but s over s square plus a square. Okay, so s over s square plus a square. From here, can you guys tell me from here? So cos 2t, can I write this as s over s square plus, instead of a I have 2 here, so 2 square. Now same way, e to the power of minus 4t, Laplace transformation of e to the power of at, if you look at here, e to the power of at is nothing but 1 over s minus a. Okay, so here I have plus a, it's going to be minus a here. So now if you look into my notes, so here e to the power of minus 4t is nothing but 1 over, so previously here I have plus a, so I have minus a there. So since minus 4, it's going to be s plus 4. Okay, so by using a linear property, I can say this as s over s square plus 2 square, which is 4, plus 1 over s plus 4. Now if I do the calculations or simplification, f of s equal to 2s square plus 4s plus 4 divided by s square plus 4 times s plus 4. Let me solve another example. Here is another example. Here we are converting this f of t equal to e to the power of minus 2t sine 4t into s domain. So as I mentioned, u of t is nothing but unit step function that magnitude changes from 0 to 1 at t equal to 0. That's what it indicates. So don't worry too much about u of t. Now, so look into look into our properties, see if we can we can use any one of those properties. So if you look at here, the frequency shift property says if I have e to the power of minus at f of t, all I need to do is find f of s, instead of s use s plus a. Okay, so that's what I'm going to do here. So sine 4t, so what is the transfer function, Laplace transformation of sine 4t by using the table? That's what we're going to find. So if we look into the table, sine function, sine at somewhere, so here you have sine at, which is a over s square plus a square, a over s square plus a square. So a is nothing but 4 over s square plus 4 square. This is what the Laplace transformation of sine 4t. Now, but I have e to the power of minus 2t. So by using frequency shift property, so the frequency shift property says if I have e to the power of minus at f of t, I can say this as f of s plus a. Okay. So all I need to do is, instead of s, put s plus a. What is a here? So if you have e to the power of minus 2t sine 4t, okay, it's look like f, but that's time domain. U of t is nothing, it's unit step function. So e to the power of minus 2t sine 4t, Laplace transformation of this equal to 4 over s plus a. So I have to put minus 2 there. I mean, so I have minus a there. If I have minus a, I end up with plus a there. So it's going to be plus 2, s plus 2 whole square plus 4 square. This is the Laplace transformation. So this is one way of representing it, or I can say Laplace transformation of e to the power of minus 2t sine 4t equal to 4 over s plus 2 whole square plus 4 square. You can simplify it. I'm not worried too much about it. Okay, so this is the final answer. I'll stop this video, but next video I'll solve more examples. Thank you.